Hello, everybody. My name is Alex. This is Slava. And we're going to give the tutorial today on geometric probabilistic models. And the way this is going to work is it's going to be split into two parts. I will give the first part of the tutorial, and Slava will give the second part of the tutorial. So at one point, we'll take a break in the middle and then switch, and that's going to be the plan. And with that said, let's go ahead and get started. So the first part of this tutorial is going to be on the background, motivation, and some technical fundamentals so that we kind of all are ready to talk about geometric probabilistic models. And just to give kind of an outline of what's going to come, we're going to talk a little bit about model-based decision-making, which is one of, in my opinion, the main motivations for talking about probabilistic models. And in particular, we're going to talk about that because probabilistic models allow you to have uncertainty in your predictions and your decision-making. And that's a really useful technical primitive to have. Then we're going to talk a little bit about geometric learning, and in particular, learning on structured data, stuff like graphs, manifolds, these kind of ideas. And after that, what's going to happen is I will switch to Slava, and he will give the second part of the tutorial, which will be on various types of geometric probabilistic models, which is the main subject of the tutorial, chiefly Gaussian processes, but also other things like Bayesian neural networks, ensembles, ideas of this kind. And this is going to include discussion on software and some applications as well. So let's get started. The idea of model-based decision-making is something that I would like to illustrate by way of an example. And the example is going to be Bayesian optimization, if you're familiar with this. So and if you're not, that's okay, because I'm going to tell you exactly what we're doing. So here we have an unknown function, which is denoted by a dashed line. And what we're interested in is, optimization. We would like to find the minimum of the function. And so the natural way that we could do this, and how we would classically do this, is, well, with some kind of gradient descent, algorithms like this. I mean, optimization theory is it's a whole field of machine learning, and even more broadly. But what we're going to do here is we're going to do a very particular kind of optimization, where the idea is going to be to build a model for the unknown function, and then to use the model in order to make decisions. And so the model in particular, which I'm denoting here, and right now there's no data. So the model basically says that the function can be the same thing sort of anywhere in space. And we're going to see how the model changes in a moment. But what the model does is it represents uncertainty about what we do and what we don't know about the function. And then once we have the model, we're going to use the model in order to decide where to gather data next, in order to balance, the trade-offs that come from the fact that we only have partial information about what the function is. And so right now, this is kind of a very boring setup because we have no data, not even one data point. So let's just pick a data point to kind of get this procedure started. That way it starts doing something. And so what happens when I get that data point is the model adapts to the data point. It incorporates the data point. And so the uncertainty around the data point shrinks. And the uncertainty that is next to the data point also shrinks, but it shrinks less than it does exactly at the data point where the uncertainty here is 0, because we've observed the function. In addition to this, you can see that the predictions also change. And so that's the process by which our model gets updated. To say this just a little bit more formally, the model here is a probability distribution over a space of functions, and we are conditioning that distribution on the fact that the function takes this value when it goes through that point. And so that's how the model works. And so that's step one of our model-based decision making. And step two is we're going to use the model to decide where do we gather data next. And so here, that's going to be done by defining a function, which is called expected improvement, if you're familiar with this. And if not, that's OK. You can just think of it as some function that sort of balances how much do we expect to gain by gathering a data point at a particular location with sort of taking into account what you do and don't know in a way that is controlled by the uncertainty of the model. And so let's just run this procedure a little bit. Let's see what it does. The first thing that it sort of starts doing is that it tries to get like a global overview of what the function actually is. And in fact, after 4 iterations, the algorithm basically finds a point that's really good. It's quite close to the optimum. And so what we can see here is if we examine the so-called acquisition function here, which tells us where to gather data next, the most promising point is going to be quite close to the point that we previously evaluated at that looked really good. And so what it's doing here is it's basically saying that let's like try to narrow down the location. And at this point, the algorithm basically finds the optimum. It took it 6 data points for this example. Now, this example is a little bit lucky. It's not always this fast, but in general, you should expect algorithms of this kind to work much, much faster compared to if you just, ran gradient descent or something, or especially multi-star gradient descent for sort of a non-convex or otherwise multimodal problem. Whereas, and so really the gain from doing this kind of quite complicated procedure where we build a model for the unknown function and then use the model to decide where to gather data next is that it's just a lot more efficient in terms of the number of points that you need in order to achieve the objective that you want. And so let's continue with this. So once we've, basically found the optimum, something interesting happens, which is in principle, this is the optimum. But of course, we know what the function is. It's the dashed line. The model doesn't know that. Instead, the model has this region over here, which sort of is a little bit lower in the dashed line, at least up to some amount of uncertainty. But it's also possible that the function is way up here because we haven't evaluated almost anything nearby. And there's only so much information that the data points that we have seen give us. And so what does the algorithm do? Well, it goes straight to that region just to confirm, is there anything better over there? And after only 2 evaluations, it says, no, this is definitely not the right region. The sort of region where the minimum is here. And if you keep running this, it's basically going to try to super micro optimize sort of what's the location, to get your floating point error down and things like this, at least at this point. And that's what Bayesian optimization is. It's an example of model-based decision-making. And in particular, algorithms of this kind sort of give you an automatic way to resolve the explore-exploit trade-off that's inherent in this problem, which comes from the fact that, you have to take into account what you know, because maybe you've seen some points that look pretty good, but you also have to explore and try other things because you haven't seen everything. And so what I want to mention here that's going to be very important for the rest of this talk is an idea that I call kind of the principle of separation for model-based decision-making, which is that this procedure where we want to sort of minimize the function as efficiently as possible and we want to balance explore-exploit trade-offs, in this formulation, it splits into a part that involves building models, making predictions, finding out kind of how does the data affect the thing that we want to find. And there's and that's really what's going on at the top of this slide. That's what's happening up here. This model is sort of entirely just telling you what do we know from the data. And then the second part, which is the part that's happening down here, is the decision-making part. It's telling us once we have some information from our model, how do we use that information in order to decide where do we gather data next? And the rest of this talk is mostly going to focus actually on the part up here, because this is ultimately a talk about geometric machine learning. And in particular, we're going to be interested in building probabilistic models. So models very similar to this model here, but where the domain is not just a number line like it is here. Instead, it could be a graph, it could be a manifold, it could be all kinds of spaces like this. And we're going to explore what is possible within that domain at the moment. So let's talk about that. Let's talk about probabilistic models. In particular, the kind of model that I used, a Gaussian process model, here, shown what happens if you train it using a method called variational inference. This is the same kind of thing you would use to train a neural network. When you train a neural network, you start with some some function going through your points, and then you run your optimization algorithm. And through running that optimization algorithm, the neural network starts to go sort of interpolate through your points, and it'll extrapolate a little bit from them as well. And what's happening here is the same thing with one difference, which is instead of finding a single curve, so a single neural network in that example that interpolates through your points and maybe extrapolates and generalizes a bit, here we're actually getting a distribution over curves. And so you can see there's a bunch of randomly sampled curves, and each of them goes through the data points a little bit differently. And it's exactly the fact that each curve that we sampled from the distribution, once we condition it on the data, goes through the data points a little bit differently, that gives us our uncertainty in this case. And the point is that the language of probability theory allows us to build things like this. So that's what we're going to do. So let's just go through a couple of different ways that uncertainty can behave, because ultimately we want to build models, and different models might do different things. So here we have another unknown function with sort of the dotted line. And what's the first thing we try to do just to see, what is this? How much does this data really tells us about this function? Which is we fit just, your completely standard, multi-layer perceptron, ReLU activation function, single hidden layer neural network. And what that gives you is this little curve that, very nicely goes through the data. And then it starts to try to generalize and extrapolate away from the data, which is what's happening here. And so you can see that what the neural network does is it tries to sort of model what happens away from your data in at least roughly a linear way. And different neural networks might do this different. But this is just predictions. We don't have any kind of uncertainty here. You just get a single curve that goes through your data, and that's all you get. So let's introduce uncertainty. Here, what I'm showing you is what you get when you use, instead of a neural network, a Gaussian process with a squared exponential kernel. It's kind of the simplest and most standard model that you might use within the Gaussian process class of models that I'll say quite a bit more about later. And here you can see that now we have these error bars that kind of go around our data points. And in particular, we can also see that the way the model tries to extrapolate away from the data is not in the same way the neural net did. Whereas the neural net sort of tried to just, shoot up in kind of a linear way to, towards the sky to try to generalize in that way. This model does the same thing locally, but then eventually it starts to kind of go back down. And the reason for this is because the squared exponential kernel is an example of what are called stationary kernels. So what does that mean? What that means, when I say stationary, what you should think of is you should think symmetry invariant. What that means is that if I haven't seen any data, then the uncertainty that my model gives me doesn't change as I move side to side in space. So it's invariant under symmetries given by translation. And that's why it's doing this, because ultimately, a priori, before I've seen any data, this particular model is going to just predict flat error bars across space the same way that the model at the beginning did. And the data convinces it otherwise, but it only convinces it otherwise when you're close enough to the data points you've seen. And if you move kind of far enough away from your data, then the model will sort of stop taking into account what the data says, at least in this particular formulation, and it'll revert to what the prior is. Now, that's how a squared exponential kernel behaves. That's how a whole bunch of other kernels will also behave, but not all of them. In fact, if I run a polynomial kernel on this example, then it instead tries to extrapolate sort of in this way. And similarly, it builds a sort of uncertainty that grows sort of a little bit, but not so much. And the point is that these are both sort of two models within the same class of Gaussian process models, but their behavior is different. And because you can get different behavior, then the natural thing to do is to try to understand how to control it. How do we design different kinds of behavior that these models could use in order to get them to be as effective as they can be for the applications we're interested in? And so I'm going to return to that in just a moment. But first, let's look at what happens when we use other kinds of probabilistic models that people use. Yet another very popular class of models is a neural network ensemble. The idea here is that, well, you have some kind of neural networks with some sort of different initialization, and you just train a bunch of them, and you see what kind of different results they give you, and you use that for your uncertainty. This model class is not, at least not directly from its formulation in sort of an obvious way, sort of a Bayesian model that involves conditional probability in the way the previous models that I showed you do, but you can still use it, you can still run it, and there are still settings where it's sort of a very reasonable thing to try. And so here, what the ensemble model does is exactly the same thing that the deterministic neural network did, except now we have sort of a bunch of different neural networks that each predict something different, and that allows you to sort of ask how many of them agree with each other and how many don't, and get uncertainty that way. You can also run a Bayesian neural network, this one using a Markov chain Monte Carlo algorithm. There are many variations of these models. Some of them work better than others. This one, at least I think, among fairly basic variants, would be considered a reasonably good one. And what does it do? Well, near the data, the sort of uncertainty that it gives is very similar to the Gaussian process. And then away from the data, it's sort of a little bit not so smooth. It kind of not entirely clear why, but people use these. They're out there in the literature, and that's kind of another example to think of. The point, again, is that different models among the kinds of models that we considered have different behavior. And as a result, at least the goal within the research area of probabilistic modeling is to understand how do we control how our model is going to behave in terms of uncertainty. Of course, we're not going to get complete control over that goal. It's a research goal. There's a lot of active work, as we're going to try to convince you in this tutorial in this area. But ultimately, what it would be very nice to be able to do is to say, this is how I want my model to extrapolate, and this is how I want it to handle uncertainty. And for sort of a reasonable kind of natural language description of what you would want it to do, to actually be able to design a model that achieves that. And so much of the kind of motivation behind some of the work that I'll tell you about in this talk is going to be from just goals like this. So I mentioned previously that the reason this model here shrinks down rather than continuing to sort of fly up is because the prior that is used for defining it is invariant under translation symmetries. And so a priori, if I just tell you, well, I want to design models that do this, it's maybe not so obvious how to achieve that. And what I want to plant in everyone's head is a very, very vague idea, which is that in order to try to regulate how uncertainty is going to behave, and generalization to some degree too, though that's kind of a little bit of a different subject, but to try to sort of regulate the behavior of uncertainty, you can think about what are these symmetries that the model is invariant under. And so the reason we get this uncertainty behavior here is because we have a translation symmetry. But of course, we can study instead, for instance, RD with a rotation symmetry or other things like this. And the behavior that you'll get if you consider models like that will be different. So that's what I wanted to tell you about probabilistic modeling, at least in terms of background and motivation. The thing that I want to tell you about next is geometric learning. And so let's talk about, in geometric learning, what kinds of things are we trying to do? Well, we're interested ultimately in nonlinear regression. I say nonlinear because we're not trying to do things like map our graph to a feature space and then, or at least to some small finite set of features and then just do something elementary like linear regression. We want to have nonlinear models where we kind of understand the way in which they're nonlinear. And yeah, how does that setup work? Well, it's pretty much the same thing as you would do to train a neural network. You have some loss function that you want to minimize. There's a typo. There should be a sum in front of that loss function, but I accidentally omitted that. But it's kind of not so important. The more important thing is that you have some x point values, you have some y values. You want to have some loss function you're trying to minimize, such as square loss. Another example would be cross entropy loss. And the other thing is that you also have some space of functions that you want to optimize over. So the space of functions here could be whatever space of functions is defined by some neural network architecture with particular kinds of random weights. A space of functions could be something like a reproducing kernel Hilbert space, or an example of which would be the space of square integrable functions with one derivative. That's kind of an example of an RKHS or a reproducing kernel Hilbert space. And the key setting we're going to be interested in geometric learning is where either X or Y carry geometric structure. So what do I mean by geometric structure? X could be a manifold. It could be a graph. It could be something else like a space of graphs. But whatever it is, it's not just a bunch of real numbers stacked together in the way that we usually do. And that's in some sense what makes it geometric. And so what we're going to be studying is how different kinds of spaces have different properties, and how do we use those different properties to build models for those spaces. So that's kind of what we want to do from sort of the classical kind of empirical risk minimization style point of view. Let's also talk about what we're trying to do from a probabilistic Bayesian point of view. Because almost the vast majority of models you can formulate in both ways. But the probabilistic way of thinking is the subject of the tutorial, but it's also a useful way to think about just model building generally. So let's just go over that briefly. Here, now we're again going to do either nonlinear regression or classification. But now, instead of just imagining we have some data and we have some loss function, what we're going to have now is we're going to have a conditional distribution for the y values given the x values and the function f. And so as before, the x and y pairs are our training data. But now we have a likelihood instead of a loss function. And the likelihood here as an example, could be a Gaussian likelihood. For example, if you knew what f was, then the y's would just be Gaussian, centered at the f of xi values, and with some variance sigma squared, which is going to be a parameter that we're either going to set or we're going to learn or something like that. And so with an ingredient like this is kind of enough to have a probabilistic approach to regression or classification. It's sort of the centerpiece behind things like maximum likelihood estimation and ideas like this, sort of going back to classical statistics. But in particular, one thing that you can do is that you could take a Bayesian approach, which is to say, well, this is a conditional distribution. And so if I pair this distribution with a prior P of f over a space of functions from x to y, well, then I get a joint distribution over functions and data. Therefore, I can compute the conditional distribution of my function given the data that I've seen. And so that kind of gives the Bayesian way of understanding regression and classification. And again, almost all models that I can think of, you can formulate in both ways. Just to give a few examples of this, you can formulate, a neural network using square loss and, I don't know, L2 regularization on the weights, just in the classical way. Or you can derive it as the so-called maximum a posteriori estimator with a Gaussian likelihood and a Gaussian prior over the neural network weights. And similarly, Gaussian processes are Bayesian models, and we're going to talk about them quite a bit in this tutorial. But if you want to think of the classical kind of loss minimization view, then a Gaussian process is, the analog of a Gaussian process is kernel ridge regression. So, there you minimize over a reproducing kernel Hilbert space, which is the sort of space of smooth functions that I mentioned earlier. And so again, here we're going to be interested in settings where the spaces x and y carry geometric structure. And what that means from the sort of probabilistic Bayesian viewpoint is that we would like to understand how do we build, well, in part, likelihoods on spaces like that. But usually that's not so complicated, at least if y is a real space. But it can be complicated if y is not a real space. And similarly, we're also going to be interested on building priors over spaces of functions, which don't necessarily map numbers to numbers, but might, for instance, map a location on a sphere to a number. So let's talk about that. So as an example, let's also talk about graphs. So a graph is a collection of nodes and edges between the nodes. And what we might be interested in modeling is we might be interested in modeling functions that take elements of the graph and send it to the reals. So let's just visualize that to understand what that is. In particular, if I take different nodes on the graph, then I'll get numbers for each of those nodes once I map them through the function. And the idea here is that somehow the kind of models that we build should take into account the structure of the graph. They should take into account the sort of connectivity in what kind of things we allow ourselves to, what kind of models we sort of allow ourselves to use and how they work and how we train them, and in particular their generalization and uncertainty properties. So, but of course, that's just one setting. And other settings include meshes. So here you have not only nodes and edges, but you also have sort of faces, and you have some way to put them into three-dimensional space. And so you might be able to, you might be interested in predicting from points on a mesh. You might be interested, I mentioned previously, graphs. Another setting is manifolds. And so here is a visualization of a manifold called projective space. And manifolds you should think of as things that are either like the sphere or the torus or hyperbolic space, basically geometric shapes of various kinds. In this tutorial, what I'm mostly going to be talking about when I talk about manifolds, because if you have a manifold, you can always discretize it sort of by and turn it into a mesh, at least, at least if it's, low dimensional enough, there's reasonable ways of doing this. So when I talk about manifolds, I'm mostly going to be talking about sort of so-called mathematically analytic, I don't know a good term for it, manifolds, which are manifolds that have an actual mathematical name. They have equations associated with them, and people sort of study them within pure math, applied math, and physics, and other domains. So usually when I say manifolds, think of these kinds of manifolds, as opposed to something like sort of the dragon manifold, which is, we represent by a mesh, even though we can think of it as a manifold. And finally, there's other things that we can think about. So in all these cases, the drawings represent scalar valued functions on the manifold, but we might be interested in things like vector valued functions on the manifold. And in particular, we might be interested in vector valued functions which are tangential to the manifold. So they sort of sit parallel to the manifold surface. And in this case, it turns out mathematically that what you actually mean when you talk about an object like that is something that takes a little bit of work to define and make sense of. And so part of, in this area, the kinds of things we're interested in is figuring out how do we do all of that. Finally, the thing that I want to mention is there's also many more examples. We will see more of them in part 2 of this tutorial, especially. So let's talk about kind of a technical challenge that occurs if we're working with things like that. And in the most basic case, we have to talk about how do we represent the data. So we have data. The data is defined on some kind of mathematical object, like a manifold or a graph. And ultimately, we want to do machine learning, which means we have to somehow put that object into a computer. And so here, in some sense, the key questions involve how do we represent the data? And let's walk through an example using graphs in order to understand what those questions look like and what are the issues in dealing with them. So a graph, a little bit more formally, consists of two sets, a set of vertices and a set of edges between the vertices. So I'm thinking about unweighted, undirected, just the simplest kind of graph that you can think about. So let's talk about how we actually represent a graph numerically on a computer. Well, the set of vertices, that's just some kind of finite set. So we can just enumerate it by integers. We could represent it in another way, but the simplest way would be to do this. Whereas for the edges, well, that's a subset of sort of the set of pairs of vertices. So what we can do is we can align all the vertices in a column, align the rest in a row, and put a number 1 if we have an edge between those vertices, and then have a 0 if we don't, in which case the edges get represented by a binary matrix. And immediately once we write this down, we can notice that different orderings of the vertices, because here we have to choose how do we order the vertices. And so different orderings are actually going to represent the same graph, because, or at least we can represent the same graph with different orderings. And what that means is that if we want predictions that depend on the graph, as well as the data on the graph, but do not depend in some completely arbitrary way on what is this choice of ordering we use to enumerate the nodes, then it had better be the case that our model is permutation invariant. So in other words, if we take the nodes and we permute them, and we sort of adjust the data and everything else accordingly, and we train the model, we would like to get the same thing as if we use the original ordering. And that's the idea here. Just to illustrate this, one use case for machine learning on graphs is in kind of the design of molecules and computational chemistry space. And so here we might be interested in taking a molecule and representing that molecule by a graph, maybe with some labels attached to the nodes and other things like this that I'm kind of not going to mention so much. But the point is that here, the ordering between these two edges in particular is different, which is why even though this is the exact same graph, and it's the same graph because it represents the same molecule, so it has the same sort of vertices and the same edges between vertices, but here we draw the vertices sort of in a different order compared to here, and that results in these edges sort of looking different, which then results in the matrices that we assemble on our computer in order to, work with data looking different because one of them is the permutation of the other. And so just a little bit more mathematically, that should be permutation matrix. That is a typo. But what we have is we have a permutation matrix which multiplies the sort of set of vertices and just permutes them. And in order to transform the edges, we have to also multiply by that same permutation matrix from both sides. And again, the reason for doing this is we want our predictions only to depend on the actual structure of the graph and not on completely arbitrary just choices of how we choose to represent stuff numerically. So similar kind of thing can occur with manifolds, where if we think about a sphere, we can represent a two-dimensional sphere by points in R3 with unit norm. But we could also represent elements on a sphere as two pairs consisting of angles relative to some point that we choose. So we pick some point like the North Pole and I don't know, somewhere on the equator, something like this. And then we talk about, what's the angle relative to that. And that's another choice of how do we represent sort of elements of the sphere numerically on a computer. And again, we would like the predictions of our models to depend on our data and not on some arbitrary choice of how we store it numerically. And understanding how to do this and sort of dealing with it well is one of the main broad research challenges within geometric machine learning. Yet another thing like this can occur with vector fields, but with a little bit of a slightly different flavor that I'll go into in just a moment. But just to illustrate it, in order to represent a vector field numerically, we might be interested here on a sphere in taking two scalar fields and then multiplying them by some kind of baseline choice of vectors. And, that gives you a basis and what's called each tangent space on the sphere. The tangent space just being, a plane that's tangential to it. And if you take these two scalar fields and multiply one of them by one arrow and one of them by the other arrow, well, then you get a nice little vector field on the sphere. But okay, here I had to make a choice of what this guy is in order to talk about what these numbers are, which means that if I take a different vector field, in this case, a rotated one, and again, the same sphere, I can represent points on the sphere in the same way. So for instance, by triples of numbers with the unit norm. But here, sort of two different vector fields multiplied by two different sort of what are called frames. That's sort of the technical term. Can give you the same vector field. And so what that means is that you have a choice of how to represent things. And so if you're doing predictions with vector fields on the sphere, it had better to be the case that your model doesn't depend on which of these choices you make. And that's going to come into play in sort of, I'll tell you algebraically what that looks like. Again, the predictions should depend on our data, not on arbitrary kind of numerical representation choices like the choice of frame. So let's talk about like a little bit of what technically that looks like. In particular, we want models that represent the symmetries of the way we represent our data, permutation being one example. The point that I want to make here is that there are actually a couple of distinct ways that symmetries can come into play sort of precisely. The first of those I showed you previously is invariance. So in other words, if you're doing something like mapping the vertices of a graph to numbers, then if you permute the vertices, then you should get a similarly defined object. It shouldn't depend on the order. So here, the idea being that transformations of the representation should leave the output constant. This should be contrasted with a related idea called equivariance. And this one takes a little bit of explanation in order to make sense of. So let's go a little bit slowly here. Here, the idea, which is that transformations correctly carry over from the input to the output. So the symmetry doesn't just change the input, it also changes the output, but it changes the output in the exact same way that it changed the input in some sense. An example of that being, if I think of this guy here and I change the numbers that are used to represent these guys by changing the basis in each tangent space, well, then I have to change these guys too. So I have to change both of them at the same time, and then that will leave the actual vector field that I have invariant. And so equivariance is about sort of changing things together, whereas invariance is about changing sort of only one thing and having the other thing unaffected. And both are sort of kind of central concepts within both geometry, but also within geometric machine learning. Now, the challenge here is model design. We want to be able to design models that respect these properties. And now this kind of starts to become much more like a well-formulated mathematical problem that one can study. For instance, how do you define a neural network whose input and output are equivariant? Again, you can, and I'll have a comment on this in a moment. So on the previous slide, I'm really talking about the symmetry properties of the way that we represent our data, but we can also talk about the symmetry properties of the model itself independently of how we represent our data. And in some sense, this is just as important. The design principle here is that we would like to have, in many cases, not always, but in many cases, models that respect the symmetries of the space. Now, what do I mean by that? What I mean is that when the model extrapolates, it should extrapolate the same way in different locations. Similarly, when the model has uncertainty, the uncertainty should behave somehow the same way in different locations. And an example of that being, if you look at this Gaussian process posterior, you can see that sort of the way the error bars grow on the left is similar to how it is on the right. And in fact, it's going to be similar everywhere in space because the model is invariant under translation. The point is that symmetries allow you to control sort of design properties like that. But we can also talk about that on the sphere. So here we have another Gaussian process model, which sort of generalizes and extrapolates by kind of reverting to the prior mean in the same way in different locations in space, because the model here that's being used is invariant under rotation. And this is even easier to see if we talk about uncertainty. So the white points here represent where I have data. And here you can see that, the way the error bars grow, so dark colors are sort of less uncertainty, lighter colors are more uncertainty, but the way the error bars grow up here is the same that they grow down there. And, you might not always want that. Maybe your space has like different levels of variability in different regions in space. So it might be the case that you want models that don't do this kind of behavior rigidly. But the point here is that at least as a starting point, this is a good principle to study in order to understand how to build models. because at least, as a baseline, you'd like to have things that behave this way. Otherwise, it's, anything is possible, and your model is just hard to understand what it does. Now, again, these ideas, they are just as relevant in the classical non-geometric Euclidean setting. But the argument I'd like to make to you is that geometric learning is, in some sense, the right technical language for studying problems like this. In particular, because you then start talking about symmetries, and you have a sort of reasonably rich set of mathematics within which to sort of probe what is going on, and a large set of sort of interesting examples that behave in all kinds of different ways with which to sort of study questions of this kind. So let's talk about models. Within geometric machine learning, specifically within geometric deep learning, the vast majority of the models that you will see if you do a literature review are going to be graph neural networks. And so what do graph neural networks do? Well, they're basically geometric analogs of convolutional neural networks. So the idea behind what they do and how they work is you think of pixel space convolution as a discretization of just some, of just a Euclidean space. So you take your nice little plane and you replace it with an evenly spaced, set of points. And then what you do is you try to replace your nice, smooth Euclidean convolution with some kind of geometric convolution, for instance, a convolution on a sphere. And then what happens is you then discretize that space and you get a graph neural network architecture where the graph comes from the discretization of the manifold. And then once you have that architecture, you can in fact go on and study, how to formulate that graph neural net without thinking about manifolds in the first place. But then we can see sort of what's the challenge with models like this, especially if we start to move beyond graphs. We want, CNNs on meshes, CNNs on other kinds of spaces, which is we need to understand what is the right notion of convolution. And, this is one of the key questions. Some other models in that space include attention models and graph transformers, various kinds of invariant and equivariant networks. These are sort of analogs of MLPs, but with extra geometric properties and tons of other ideas. And I'm not going to go into them in very much detail in this tutorial, because there's a very nice book by Michael Bronstein, Jean Bruna, Taco Cohen, and Petar Velichkovich, who study those questions actually in a fairly substantial amount of detail. And so check it out. It's a really good resource. You can find it online. It's sort of available free. There's a bunch of slides. They have the slides they have in particular are really, really good, in my opinion. There's also video lectures from a recent lecture series that was given at the African Institute of Mathematical Sciences by at least one of the authors, I think maybe all of them. But this is, I don't recall exactly, but this is a resource that you can use in order to study how geometric deep learning works. So those are the main things I wanted to tell you about. And in the last few minutes of my part of the tutorial, at which point we will take a break and we will switch to Slava for his part of the tutorial. But, and I'm also happy to take a few questions during that break. But here, the thing I wanted to show you is just some really impressive applications of geometric machine learning and geometric deep learning in particular. So in this work, which is published in Cell, the sort of biology journal, a graph neural network basically was used to predict antibiotic activity in a whole bunch of different proteins And in particular, it predicted that for a protein called halicin, which had been previously studied as a diabetes medication. And I don't know if it had any success in that. But what these authors did was they took that protein, they actually synthesized it, tested it in mice, and it was found that it actually did have the predicted antibiotic activity. And moreover, the way that it achieved this was sort of structurally distinct from other kinds of antibiotics that people study. And the authors were very excited about this as sort of an angle of attack by which to deal with antibiotic resistance. So sort of here's a figure, part of which illustrates the use of a graph neural network for those predictions. Now, there's many moving parts beyond just the graph neural net, so we can come to that. But the thing I wanted to share next is yet another application. So Amazon uses a system whose name I'm forgetting, which is graph neural network based to do some of its product recommendations online. And so if you're shopping on Amazon and buying, you look at this little list that sits beneath whatever product you open, and they show, here's some other relevant stuff that you might also buy if you're buying this. Well, at least as of a few years ago, there's a paper from 2020 that describes a graph neural network-based system, which the authors say was a substantial improvement on top of whatever their previous approach for doing this was. Yet another application that's kind of pretty high profile is ETA prediction in Google Maps. So if you use Google Maps to get from one point to another, then the more recent system for doing this, as of a couple of years ago, actually uses graph neural networks in order to predict when you're going to get there. And this system was found to be substantially more accurate compared to sort of the previous state of the art that Google was using before that was deployed. So, in some sense, these applications, it's worth a lot to these companies and the scientists that I mentioned. Of course, I'm cherry picking kind of the most sophisticated ones to show you. So there's a lot of other kind of less exciting applications as well. But I think the fact that this is possible kind of gives us reasons to be excited about geometric learning as sort of a broad area of studying. And so with that, I'm going to conclude part 1, and I'm happy to take questions. And we can also, if anybody wants to take a break and, I don't know, walk for 5 minutes, we'll break for maybe about let's say 10 minutes or so. But I'm happy to take questions, and I saw a hand in the back. What can I do for you? Sorry, could you please repeat the question? Symmetric by extrapolation. So you'd like me to define what is a symmetry, and you'd like me to define another thing that I couldn't hear what it was? What I mean by extrapolation. No, what you mean by symmetric by extrapolation. Yeah. So let me answer kind of in 2 ways. The short is, if you want a rigorous mathematical definition of what these things mean, that takes some time. And so I can't do that right in the middle of a tutorial because I would have to write a bunch of stuff down, and it's a little bit time limited. But what I can do is I can give you sort of some examples. And I think based on the examples, we can either work backwards to get a definition, or you could, there's a whole bunch of books that kind of talk about these things. The geometric deep learning one being one of them, that will have these proper definitions for what this means. But the idea of a symmetry is somehow the idea where I take my space, I do something to it, like rotating it or moving it around or something like that. And the space that I get as a result of doing that is the same space that I started with. So for example, one example being you take the sphere, you rotate it, and when you rotate the sphere, then the kind of space you get is similar to the sphere that you started with. So that's kind of a way of thinking about rotation. Similarly, you can do the same thing on a circle, you can do the same thing on a plane, and that's the sort of notion that I mean. What I mean also by extrapolation is just how does your model make predictions in areas that are some distance away from your data and where there's no data point nearby. And I don't mean that in any kind of precise mathematical sense. That's more of sort of a human language, like useful way of thinking about what a model does. But if you want to put it into precise mathematics, you can study things like, generalization bounds. But there, the kind of gap between intuition and like actual formalism is a bit bigger. Do you want to take the question too?
Thanks. Maybe I can.
It's a really good question, by the way.
Yeah.
You have
maybe
to...
maybe I can add something. Sorry for the sound burst. Just sort of to the question of what the symmetry is. It's whatever you decide it to be. This is sort of the basic idea, and you define symmetries in your own preferred way, and then you make models respect them in a way of being invariant or equivariant, right? So depending on the problem, you will have different symmetries that will be natural for the problems. And for different types of geometry, there are different sort of canonical classes of symmetries. For example, if you're working with vectors in the Euclidean space, the canonical symmetries would be translations and rotations, and you would expect models to respect them. For example, that if you translate your data set, then the model that you will train on the translated data set will be just the translation of the initial model, something like this. But you can also supplement this, but by an additional class of constraints. So, for example, you may say that you're interested in studying periodic functions, right? And then you can supplement this symmetries with the constraint of invariance with respect to translation by, say, 2π, and then only care about models that satisfy this, that doesn't change at all. So the first example was about equivariance, when like sort of translation corresponds to another translation. And here is another example where translation corresponds to the same thing. It doesn't change a thing. But the main idea, symmetries is whatever you define them to be, really. Are there any more questions? Yes. Should I take this one first? Okay.
So you may be interested in both cases, is at least but the question, so just for anybody online, the question is, where do we want to enforce symmetry constraints? Do we want to do it at the point where we define the model, or do we want to do it within the sort of algorithmic training procedure that we use to train the model? And the answer is you might be interested in both cases. It depends on what you're doing. Part of what determines that interest is A, what you want, but B, also how difficult it is to achieve. You could, within the Gaussian process models that we're going to talk about, the design constraint on symmetries is really going to be at the level of the model. And once you have it at the level of the model, then you try to figure out how to do compute using the objects that you get and sort of make it actually work numerically. But you can also do things like Bayesian neural networks, where you have regularization to enforce particular kind of symmetries. And what can happen is that for a particular case, one of these ways of doing things might be a lot easier to do than the other way. So it's sort of case dependent, but they're both of interest. Do you want anything?
Maybe just one example of the training side of things and how it might be difficult, although it's not always difficult. If you have, say, permutation invariance, what you might try when training is just to produce many permuted versions of your initial graph, and then add this to your training data set to make sure that the prediction is the same for all of them. You can totally do that. The only problem here will be that there is factorial of these permutations, and it would blow up your data set quite quickly. But there might be other ways. This is a good question. You're quite right that you can enforce these things at both of the stages. Any other questions, maybe?
Just to mention the technical term, the latter idea, which is adding different kinds of transformations to your data, more commonly known as data augmentation. I guess we have many questions. I'll take Georg in front.
So you talk about uncertainty, and you showed a lot of examples of how different architectures estimate uncertainty in different ways.
Mhm.
And you do all of this probabilistic modeling to get some kind of estimates of uncertainty, but like what tells apart the good uncertainty estimate from bad?
This is a very good question. I mean, the thing that and the answer is that these are all modeling questions. So what you actually mean by uncertainty is going to depend on what you're trying to do, what kind of problem you're studying, what kind of data you're working with, and what your goals are. And in fact, I actually really like the question, which is in part because this is exactly the kind of thing that I want like everybody to think about when they see the ensemble, the Bayesian neural net, and the Gaussian process. Because in some sense, what the ensemble is doing is different from what the Gaussian process is doing, even though they both produce kind of nice little error bar looking things. And whether or not that's useful kind of for you is going to depend on what you're trying to do. The best way I know for one of the best ways I know for studying that is using kind of the mathematics of regret analysis, which within a decision-making framework, but this is beyond the scope of what we'll talk about, even though I think it's very, very interesting. But yeah, I think that's, so thank you for the question. We maybe have time for one more. I see one hand in the very back.
So I am going to ask about the types of uncertainty areas. So there is regulatory and uncertainty. And I'm not sure which one is being able to.
So, and the answer is both and neither, in the sense that uncertainty is a very broad thing that I think is really hard to categorize in like a clean way. The distinction between aleatoric and epistemic in a setting like this, you could mathematically interpret as kind of the distinction between your likelihood and between your prior within a Bayesian framework. But then you might be interested in talking about that concept not in a Bayesian framework, or you might be interested in some kind of other model where the sort of uncertainty you get out of it doesn't sort of split cleanly like that. So one of the broad messages that I think we have is that uncertainty is not a simple thing. There are many ways of thinking about what you actually get, and the best way of understanding it in some sense is to think quite a bit about the mathematical details of what the setting is. The main thing that we want to say is, among all the notions of uncertainty you can think about, many of them are well represented by probability. And once you have probability, you can start giving formal notions to ideas like aleatoric and epistemic. And so, and in some sense, the questions that we have are how do you build models that let you do all those things in the first place? And the question of sort of understanding uncertainty further is sort of really a question for probabilistic modeling broadly, and even more beyond that for non-probabilistic kinds of modeling as well. But it's a really, really good question. Actually, it's so good of a question, I can't give you just one clean, quick answer to it. So, but thank you very much for that. So I think with that said, let's set up the microphone again, and we're going to move to part 2.
Sounds Sound check. 1, 2, 3. I hope it works. Okay. So yeah, hello, I'm Slava, and I'm going to present the second part of the tutorial. Thank you very much, Alex, for presenting the first one. The first one was more about doing a broad and sort of zoom out overview of the related concepts. The part 2 that I'm going to present is going to be much more sort of concrete and zoomed in. And so, yeah, let's get to it. So you already saw the outline for the first part, and you already saw the first part, so I will not repeat that. As for the part 2 that I'm going to present right now, it will contain these 5 parts of very unequal sizes. The first part will be about 3 sort of basic types of probabilistic models, and trying them out on an example problem. The second part will be about a deep dive into one concrete class of probabilistic geometric models, deep Gaussian, geometric Gaussian processes, I'm sorry, which I would try to persuade you are good baselines to start geometric probabilistic modeling from. And also this is why sort of we concentrate on them in particular. Then I will talk about some emerging applications of, again, geometric probabilistic models. We already saw that there are very impressive applications of geometric deep learning. Obviously, there are impressive applications of probabilistic modelings in the sense of decision-making, like Bayesian optimization. But there will be a couple of examples about having these things combined. In part 4, I will talk about software considerations. So if you want to get to it and try your geometric probabilistic modeling right away, what tools can you use? And then there will be summary, which I will turn back to Alex, and it will be a very short portion, after which we will take some more questions. So this is the outline. Okay. So as promised, first section is about basic types of probabilistic models. And arguably, if you define basic as most used and most famous at least, then these are the following ones. First, Bayesian neural networks. Second, deep ensembles. And for these two, if we are going to deploy them in geometric settings, to say more concretely, in a setting where inputs are not vectors anymore, but something different, perhaps nodes of a graph or points on a manifold. For these models, we will have to think of specialized neural network architectures. There is a third type of probabilistic models, Gaussian processes, which are different in the way, in what we should change for them to work on these non-Euclidean domains. They would require specialized kernels. Okay, so there are these 3 types of models that people use very often. And now I want to take an example problem. It's actually, I would say it's a new problem. And I will try to take a sort of off-the-shelf tools that are available for each of these classes of models and see what happens in terms of the prediction quality and uncertainty quantification quality. Let me introduce the problem. So this will be a regression task on the node set of a graph. This graph is the graph of San Jose highways. It has about 1,000 nodes, and it's visualized right here. And notice that in the corner, we have a zoomed in interchange to be able to examine more finer behavior on the future plots. Okay, so on this graph, we have 325 measurements of traffic speed. There is this performance measurement system on California highways that just freely offers the data sets of speed measurements across the highways. But of course, sensors are actual physical objects, so they are not as dense as we want them to be. So we only have this data in part of the nodes. The nodes that remained white are actually, we don't know any data whatsoever. From these 325 nodes, I want to exclude 75 for test data set, and I will retain the 250 for training purposes. And this 75 will help me to also get perspective on how models perform in terms of the numerical metrics. Okay. One last thing is that since I will be showing predictions in the future slides, I want to mark the training locations with these black bullets so that we can distinguish them from the predicted values. Good. So let's start with a simple, well, actually trivial baseline. Let's see what happens if we just predict an IID random variable whose mean is just the mean over the train set and whose variance is just the variance over the train set. So here we have the data as in the previous slide, and this is how prediction would look like, the constant, right? And it's right in the middle of the color bar, which is, by the way, in miles per hour. So something very interpretable. And if we compute the RMSE score, it will be right here. We can do the same with uncertainty. So I visualize standard deviation of the predicted random variable here. It will be just the standard deviation over the data. So basically at the very top of this color bar. And in order to measure the performance numerically, I will use the negative log likelihood score. This is just one of the many ways you can measure the calibration of your model, measure somehow quantitatively measure how good uncertainty quantification works. I will use this one just to take something. So great. Let me turn to the promised. I'm trying out now different probabilistic models. I think this is a typo on this data set. Before that, though, oh no, and let me also tell you that the code for everything will be available at the end of the talk, and it's actually I hope that maybe you can try using these simple models and maybe even improving on what I'm showing you here. It should be very simple to use, and the intention was to sort of give you a nice starting point on how to experiment with the geometric probabilistic model. So I start with a sanity check, though. So I want to take a deterministic graph convolutional neural network, something from the geometric deep learning world, and make sure that it can at least do the prediction part properly, because if it cannot do predictions on the data set, there is really no hope it can do uncertainty quantification well. So let's make sure it works. And here, again, the data set. And if I take just the simplest possible thing, graph convolutional neural network with just one hidden layer, the prediction will look like this, which is much better than the trivial baseline. The RMSE is also considerably better. But I can also remember the standard notion that depth helps with the neural networks. So if I take 7 intermediate layers, I can improve even more here. And notice that it might be a little bit hard to see on the picture itself how the prediction is different. This is not that important because you can track the numerical metric, first of all, and second of all, this will be more important to look at the picture for the uncertainty, not for the predictions. Although, if you pay close attention to this part, you can actually see that it changes, and it changes for the better, in the sense that for the deeper architecture, the values along one of the sides of the highway are consistently purple-ish, and the values in the opposite side are consistently orange-ish, which is what they're supposed to be. And if I go back, you can notice that here you have much more orange values along this purple direction of the road. And this is just because, you know, this is this time of the day when everybody is moving in one direction. Because of this, there is much more traffic in this direction, and cars are going slower, and in the opposite direction, it's much better. So a very natural phenomenon, and this is exactly the point to look for in terms of geometry of the problem, right? Because there are these nodes which are on the picture located very close to each other, but in terms of the intrinsic geometry of the space they live in, they're actually very far away. To travel from one side of the highway, you know how long can it take to travel to the other side of the highway. This is prediction on the whole graphs, on the whole graph. Yes, it's on the train. Oh, on the test. Sorry, I selected this 75 points of test data, and the metrics are reported on the test set, of course. Okay, so yeah, we have this graph convolutional neural network, which works well, I would say well for prediction, especially the deep one. It is able to capture the geometry. So great. Sanity check complete. Now we can actually try probabilistic models. And I will start from the models based on neural networks, and in particular with deep ensemble, because it's the easiest if you already constructed a neural network architecture, right? To deploy an ensemble, you just need to train this architecture many times with different random initializations, and then just combine predictions to get final prediction and uncertainty. So it's very simple to implement. It's considerably harder in terms of training than some other models. What I mean is like how much time it takes to train this. But in this simple problem, it's actually okay. So I'm considering deep ensemble. Here is again the data set, and I will take exactly the same neural network architecture that was on the previous slide, this 7 intermediate layer neural network, and we'll train ensemble based on this one. And ensemble will be constructed from 100 models, I believe. So what happens here is prediction is still good. It is a little bit worse than for the single neural network. And the reason for this is very simple. I'm showing here in this leaderboard the results of the best run across several runs. So since Ensemble averages multiple runs of this same neural network, it's natural that neural network performs just a little bit better in terms of the metric, but not actually in terms of like any qualitative behavior. But what's great now is that we have an ability to quantify uncertainty. The initial neural network wasn't able to do that, and Ensemble can. And so now let's look at what uncertainty turns out to be for this model. Turns out to be this, and it's actually terrible. So basically what happens is that predictions are quite consistent across the random initializations of the ensemble, which causes the model to be very overconfident in its predictions. So the uncertainty is right at the bottom of the color bar. And if you measure its negative log likelihood score, it's actually worse than the baseline, worse than the noise that we tried first. I'm not saying that it's impossible to do to make an ensemble that will output reasonable uncertainty, and I very much encourage you to try doing that. But if you just take this off-the-shelf architecture, combine it into 100 neural networks to make an ensemble, this is what you get. The second type of probabilistic models will be Bayesian neural networks, and we'll be deploying them to the same setting. So again, I will take the same architecture of the neural network as before, and I will make it Bayesian by assuming IID Gaussian priors on the weights, use some initialization like neural network based in classical initialization of the variances, and this will be it. Again, our data set, and let's see what happens. And I'm using here MCMC to train Bayesian neural networks. The reason is that arguably it eliminates some bias that is presented by choosing a particular variational inference technique, but also to just pick something. So if I run MCMC here on this architecture, I again get something terrible, even worse. So even prediction is terrible. It's way worse than for the trivial baseline. Uncertainty is again terrible, and it's just not certain in anything. But the reason is not because Bayesian neural networks are that bad. It's just because MCMC didn't converge. Something that I'm sure you experienced before. But all is not lost in this example. I can actually make it work by just reducing the size of the model. So I will simplify the problem for MCMC. I remember that depth is important for neural networks, so I will not be decreasing the number of layers, but I will be decreasing the width of the layers. So instead of 100 neurons per layer, I want to take 10 neurons per layer. And if I do this, I get something much, much better. Now MCMC converges. And in terms of prediction, I actually get exactly the same score as for the ensemble. And but the thing that we are interested in most is uncertainty. So let me get right into it. So uncertainty now is in a reasonable band, which is a great success compared to what we saw before. So it's not here and it's not here, it's somewhere in the middle. And it's actually not constant. It's just that color bar is rather wide. This is why you cannot see that clearly how it changes. It's not great though in terms of it being so concentrated and so similar to a constant. And also it's not that great if you just examine it more closely and notice that, for example, here you can observe points where you have data and which are associated with higher uncertainty than neighboring points that don't have data. So still not the perfect thing. Again, very much encourage you to try and improve this example. But this is what you get from investing sort of, I don't know, 4 hours into this. Okay, now I'm turning to the last class of models. And yeah, the hopes are low now. But maybe we will have something reasonable in the end. And actually we will, I will like spoiler this out for you. But the reason is also quite explainable. So I will take a Gaussian process, but not just a Gaussian process. I will take one of the what I call geometric Gaussian processes, a Gaussian process which is specifically tailored for doing uncertainty quantification on geometric domains. So this is Gaussian process endowed with the geometric analog of the usual Matern kernel. I will talk in depth about what these are later on, but this is supposedly a good model specially designed for geometric settings, though not for this particular one. So it's not that that bad in terms of problem being like things being unfair. So again, the data set, let's try to make a prediction. Yay. We are the best here. And now we come to uncertainty, which is finally something very much giving you intuition into what happens in on this particular example, right? So for example, if you are looking into the problem of modeling this in order to establish the best places, the optimal places to put new sensors at, from this picture, it's immediately clear where you would do that. There are these yellow regions where there is no sensor coverage. And if you have maybe 4 new sensors to distribute, well, 1, 2, 3, and maybe 4, these tails of the roads are the obvious solution. Also, in terms of NLL score, we are quite good here with Gaussian processes. So again, this is not because Gaussian processes are great all the time, regardless of any other parameters of the problem or the particular Gaussian process model design. This is not that. And I'm actually going to show you that not all Gaussian process models work well on this particular example. I can dig up literature on kernels, on structured domains, which was a very prominent topic back in 2000s, and take a couple of these kernels instead of this geometric Matern kernel. And let's see what happens if I do that. So first, I'm showing you the picture from the previous slide. Second, I'm using what's called random walk kernel. This random walk kernel, again, gives us, well, arguably in terms of picture, maybe something better than everything but the last Gaussian process that we saw, but still considerably worse than the last one. Because, for example, here, although actually data density is enough, there is a lot of uncertainty here. Also, prediction gets worse, right? So we are here now, and NLL score is here right at the level of Bayesian neural network. I can choose another kernel, say one which is called inverse cosine kernel. If I use that one, then I actually almost perfectly reproduce the performance of the baseline in both prediction and uncertainty. So not all Gaussian processes are great, but some of them maybe. So to summarize, a way to think about this example is, first of all, that I'm here presenting you a new, easy to use and visualize benchmark for regression on geometric data. And if you're interested, or if you get interested maybe after this tutorial in studying this, this will be, I think, a very good starting point. Second is that there is this class of geometric Gaussian processes, which is representing a set of reliable off-the-shelf probabilistic models. The behavior that I just showed in this particular example is something that happens not just for this particular data set. It happens quite often. And I want you to think about the situation as the analog of the situation in the Euclidean case, where you have maturing Gaussian processes or RBF-based Gaussian processes, which are very good baselines that you would typically start from. If they fail, if they are not powerful enough, you will go for something else. But here, there is this class of models that reproduces the same sort of, that occupies the same niche, that this is reasonable object to start from, off the shelf baseline. So you can also use these models to benchmark others against, and this is what I encouraged you to do, right? Take the ensemble or Bayesian neural network examples and maybe try to make them work better. Good. So this is my introduction and in part motivation of this class of geometric Gaussian processes. Now I want to spend considerable time to introduce this class and to show you some bits of how it works, how it looks to use those, and how it looks to sort of research into those. So let me start with that. So I want you to think about some geometric domains when I will be talking about these geometric Gaussian processes in the next few slides. And this will be, so think about graphs. First of all, something that we just saw now. I mean, node set of a fixed graph, something like this. Think about manifolds, that you are modeling a function whose input domain is a manifold, output domain is just reals. And maybe think of this third thing, which is spaces of graphs, and which corresponds to the situation when you model functions that take whole graphs as inputs. So for example, as Alex have mentioned, graphs are used to encode molecules, and you might think of functions representing some property of a molecule, right? Something like this. So these are examples of geometric settings. So mapping inputs from one of these to just reals that this class of geometric Gaussian processes will be a model for. Good. So now I want to remind you about this class of standard kernels that people just typically use in Rn unless they really know what they're doing. These are maturing kernels given by this somewhat cumbersome formula that you don't need to get into details of. The most important things about this formula, if you never saw it, is that it's parameterized by three very interpretable parameters: by variance, sigma squared, which basically scales the y-axis; by kappa, the length scale, which basically scales the x-axis. And finally, by nu, the smoothness, which determines how many derivatives the resulting Gaussian process will have and the resulting kernel will have. So for example, if you visualize the samples from Gaussian processes with these kernels, you can see how smoother they become when parameter nu gets larger. Actually, when parameter nu gets very, very large, you get in the limit probably the single most popular kernel and Gaussian process out there in the literature, in machine learning, in statistics, in kernel methods, you name it, it will be the most popular thing. It's defined by this simple formula, just like the Gaussian density, and it corresponds to infinitely differentiable Gaussian processes and infinitely differentiable kernels. Okay, so this class of models, and by the way, I am including the RBF kernel into the class of maturing kernels, saying that this is just an element with nu equal to infinity. So when I say maturing kernels, this in general means that these are the proper maturing kernels plus RBF. So this family of kernels forms this baseline set in the Euclidean case. This is what you typically start from. And so the way in which it seems reasonable to approach the task of designing the same kinds of models in geometric settings is to try and generalize the maturing family to these different settings. There is, of course, many ways in which you can do this. And probably, if you think about this for 5 seconds, you will come up with something that I call here distance-based approach, which is basically, let's look at this formula. Let's notice that it only depends on the distance between the pair of inputs. And then let's say if we have some geometric input domain, probably there is some notion of distance on this geometric input domain. So why don't we just substitute this Euclidean distance with our sophisticated geometric distance and get something like this? This is a very natural idea. Actually, sometimes it can actually work, but there is a very big problem with this idea. Although it is geometry aware, and by saying this word, I mean that it respects the symmetries of the space. Respects the symmetries here means that if you are on the node set of a graph, for example, then there is the natural set of symmetries, which are automorphisms of this graph. If you're on a manifold, there is natural set of symmetries, which is isometries of this manifold. So you can replace the standard Euclidean translations with these automorphisms or isometries and ask your kernels to be invariant with respect to automorphisms or isometries. You will get this generalized stationarity, and this is what I mean by geometry aware, actually. So these are geometry aware kernels in the sense of respecting the symmetries, but it turns out that these are not actually well-defined kernels. So you can prove for manifolds, for instance, that such a formula doesn't define a kernel unless your manifold is isometric to Euclidean space. For the node set of a graph, you can prove, and this is a very old result, that it's not a well-defined kernel unless the nodes of the graph can be isometrically embedded into some Hilbert space, which is a very restrictive assumption. The third setting, the spaces of graphs, is a little bit more involved because there is no standard definition of what space of graphs is. So I will just postpone this until after I am able to talk a bit more about this. But all of this sort of suggests that we probably need to find a different way of generalizing this Matern family, right? The thing that you come up with in the first 5 seconds of thinking about this is very natural, but unfortunately doesn't really work. There is an alternative path. Yes. It's not positive semi-definite. Yeah. Yeah. Yes, it's not occurring. Yeah. So the question was, what was exactly meant by not well defined, and the answer is not positive semi-definite. Yeah. Thank you for the question. Good. So there is another approach in which you can tackle this problem, which is based on stochastic partial differential equations, which in this specific instance are not that scary as they usually are. And it also goes back very long in time. So it goes back to the result of Whittle in the 60s, saying that the standard Euclidean Matern kernels are kernels of the Gaussian processes that solve this particular stochastic partial differential equation. So here, delta is the Laplacian operator on Rn, W is the Gaussian white noise, and D is the dimension of your Euclidean space. This is a characterization of the standard Euclidean Matern kernels. You can use this characterization as an alternative definition. Actually, these are equivalent definition in the Euclidean case. But what's good about this alternative way of defining them, as opposed to just defining them via the formula, is that this way generalizes well. It generalizes well because the objects you need to define in order for this to make sense have analogs in different settings. So, for example, the Laplacian has the analog of Laplace-Beltrami operator on the manifold, or it has the analog of graph Laplacian on the node set of a graph. White noise is also typically very easy to generalize. So is dimension. And so something that I propose as the alternative direction is to use this stochastic differential equation based definition as a foundation, and then just change the meaning of the objects inside this definition. This is actually something that was proposed about 10 years ago in a paper by Lindgren to generalize this to the Riemannian manifold case. Good. What I can also say about this way of generalizing Matern kernels is that this is easy to prove, but I will not do this. This gives you something that also respects the symmetries of the space. And something that which is very easy to prove, which is obvious, is that this always gives you a positive semi-definite kernel, so a well-defined kernel. And the reason is you are defining a Gaussian process, not the kernel. And if you have a way of defining a Gaussian process, then the kernel will always be a valid kernel. The problem with this definition, though, is that it's implicit. So you have some equation, but you don't have the formula for a kernel. In the previous case, it was trivial to use the formula. And here, it's absolutely unclear how you would even approach modeling with these Gaussian processes. One obvious idea is that you can discretize domain and maybe try solving this equation in some clever way, which is actually a prominent research direction in what people do. But this has very limited applications in sort of low dimensional, smaller structure, because you need to work with grids. So having introduced this, I want to state that this is a good way of defining the analogs of Matern Gaussian processes. And the only thing we need to resolve for this to be practically usable is to make the definition explicit And by this, I mean to give ways to compute the kernel point-wise and perhaps introduce some other computational primitives that I will not be talking about in detail today because of the restrictions of the time. So I want to take, only if the question is very quick, because it's better to postpone most of the questions until the end. If it's very quick to the content of the slides, then.
Does it need a boundary condition?
Good question. So the question was about boundary condition for the differential equation, and the answer is it depends, because the typical definition of a manifold, for example, is a manifold without boundary, and so no boundary condition is needed. If you're working on a sphere, there is no boundary. Again, for the graph, there is graph Laplacian, which doesn't require you to introduce any sort of boundary. You can consider domains which require boundary conditions, which in a way you can think of as specializing the Laplacian operator. There are ways to think about this in this way. So sort of, you still don't need to choose the boundary conditions, but you need to adjust your operator. I don't want to dwell on this too long, but yeah. So by default, we just don't need boundary conditions. Okay, so now I want to take this one setting, the setting of the node set of graphs, of a fixed graph, and show you how you can make this definition explicit in this particular setting. So here, the motivating example is basically what we just saw before. I actually was using these exact maturing Gaussian processes that come from this exact definition in the example at the beginning of the second part of the tutorial. Okay, so say we have a particular kind of graph, a weighted undirected graph. The fact that it's undirected is actually a very, so this is not a technical limitation that you can easily bypass. And if you think about this, this is a very natural limitation to have. So say I have a weighted undirected graph, I will also assume that the weights are negative. And in this case, if you replace the Euclidean Laplacian with the graph Laplacian operator, which will be a matrix in this case, if you replace the Gaussian white noise with just a vector of IID Gaussians, which is the natural way of defining Gaussian white noise on the discrete domain. And finally, if you put the dimension to be equal to 0, because there is no easy way of defining dimension on the graph, and this is actually one of the cases where the dimension generalization is somewhat hard. But 0 is one of the ways in which you can do this. Then the SPDE that you had before turns actually into a stochastic linear system. And you can solve this stochastic linear system using basic undergraduate linear algebra techniques. And the solution will be a Gaussian process with the kernel of this form. So here you have a summation over with the number of terms equal to the number of nodes in the graph. Here you have some coefficients, and these are sort of basis functions. And this is a Mercer type of decomposition for the kernel. And these basis functions Fn are basically eigenvectors of the graph Laplacian reinterpreted as functions, while these guys are some simple functions of the eigenvalues of the graph Laplacian matrix. And the simple functions are really simple. So as simple as these explicit formulas. So basically, here you can just solve the equation conditioned on the fact that you are able to compute these guys. which can in principle be a numerically hard problem to solve if your graph is large enough or if it's not a sparse graph. But if your graph is small enough or sparse enough, then this is something that you can do quite efficiently. And then you can just stack up the primitives here and get the kernel by this formula. Also, you typically don't need to sum up everything here because as in all Mercer decompositions, these coefficients can be ordered in the decaying way. And you can truncate the decomposition, getting a very good approximation in many, many cases. So this also allows you to use a approximate technique for computing eigenvalues and eigenvectors of a matrix, which only give you top 100, say, of these eigenpairs of the matrix. You don't need to compute all of them. Okay, so with this, and again, this is exactly the machinery that was used in the example before. And this is machinery that will produce the kernels that look like this, for example. And here is a simple grid graph and the kernel, which is like this bump around the point, right? So one point is fixed and the other point is not fixed. And this is what we are visualizing here. So star graph, cycle graph, something very intuitive, but guaranteed to be positive semi-definite and actually respecting the symmetries in being invariant with respect to automorphisms of the graph in an automatic way. Okay, so you can do this for the setting of graph. Actually, I would say that the setting of a graph is perhaps the easiest setting to make things explicit. And I just want to give you some notion of what happens in some other settings. So I want to start with the setting of compact manifolds, which is actually quite simple, similar to the setting of a graph, and where the formula that you get, let's just look at the top part first, is again very similar, but the summation is now infinite. So say you live on a sphere. This is what happens. Here, what happens differently is that, first of all, we have infinite summation, and lambda n and fn are now Laplace-Beltrami operator eigenpairs rather than some graph Laplacians eigenpairs. And there is an infinite number of these guys. And second thing, and this is an interesting phenomenon which sort of appears in the case of certain well-behaved manifolds, which almost never appears in the case of graphs. This is the fact that eigenvalues very often correspond to a whole lot of eigenfunctions. The same eigenvalue corresponds to a lot of different eigenfunctions. And so you can group a part of this expression into this separate inner summation. And it turns out that for manifolds, very often there are independent ways of computing this thing, which don't require you to actually compute these. And this is, I would say, the second most important thing of what happens on manifolds, like, for example, on the sphere, that you have the ability to group eigenfunctions and sort of merge them together in something more simple to compute, and also getting an expression which converges even faster than the first expression. For example, in the sphere, the eigenfunctions are so-called spherical harmonics, a very widely known object. And these groups of products of spherical harmonics by the addition theorem for the sphere and the hyperspheres, this group of spherical harmonics corresponding to the same eigenvalue, this summation will be equal to what is called Gegenbauer polynomial, which is just a family of polynomials that you can compute, well, I don't know, it's a standard thing in SciPy, for example. No need to compute spherical harmonics, just compute Gegenbauer polynomials, very easy to use. This is just to give you an idea of different settings being similar in a way, but also different, and different phenomena appearing in different settings. Now, to give you a couple of more examples, first thing is non-compact manifolds. Think about the hyperbolic space. Maybe you want to, I don't know, put your data set in some hyperbolic embedding and do something on top of this. Or yeah, think about a hyperbolic space as the most natural example. It turns out that there is also machinery to sort of make things explicit, but there is no summation now. Instead, you have an integral which is intractable, but can be approximated using Monte Carlo techniques. And this is very, very similar to random Fourier features, where you can where you can represent your kernel in terms of Bochner's theorem as inverse Fourier transform of some spectral density, and then just subsample this integral. In the case of random Fourier features, this is a famous technique for speeding up computations for kernel methods and Gaussian processes also in particular. You have the ability to compute the kernel in closed form, but you choose to compute it approximately through random features to be able to apply some additional speed ups. Here, in the case of non-compact manifolds, you don't have the way to compute your kernel in closed form, but you have random Fourier features still. So you are able to approximate it using this technique. And also, you always get guaranteed positive semi-definiteness. So you can just plug this and play and apply to your use case right away. Another very different setting is spaces of graphs, something that I mentioned in the very beginning. And here, the difficulty comes from maybe a somewhat unexpected way. And this is the fact that before, when we were talking about node set of a graph or a manifold, these were geometric objects to start from. There is very well-defined geometry of a Riemannian manifold. The Riemannian structure defines this geometry. And for the node set of a graph, the adjacency matrix defines the geometry. It defines, for example, the graph Laplacian operator. It defines the distance. It defines the set of automorphisms which serve as natural symmetries. But if you are working with a set of graphs, something that encodes your molecules, for example, there is no standard structure. You typically start from a set. And you have to endow this set with geometric structure first in order to be able to derive in this unified way the analogs of maturing Gaussian processes, maturing kernels in this setting. And what I want to tell you here is that there is a good way of doing this, of defining this geometry, and there is a bad way. So the bad way is again distance-based. So you can say, I will introduce geometry by introducing a distance. This unfortunately doesn't help because, well, it's very difficult typically to build kernels starting from a distance function. They just don't become positive semi-definite. What you can do alternatively, though, and this is what I really suggest you consider if you haven't before, is that if you're faced with a problem like this, when you have a discrete set and you want to define a geometry, you do this by means of making this discrete set into a node set of a larger graph, right? So for example, say you went ahead and defined some distance function. Instead of just using this distance function, just say, I will connect by an edge every two elements of my discrete space if and only if they're distance one from one another, right? This will be another way of defining geometry on the same set, but this way will automatically yield you the class of geometric Matern kernels, because basically it will be as the nodes of the graph setting that we just considered before, right? So then Matern kernels, and heat kernel here is what people also call RBF kernel, like these kernels are automatically defined if you define geometry in this way. There is another difficulty that comes into play, though, if you use this, and this difficulty is computation. Because if you're working with a set of graphs, I don't know, consider the set of graphs of all graphs on, I don't know, 10 nodes. It will be exponential in size, right? So of n nodes, it will be exponential in n. And this means that the graph Laplacian matrix you will have to deal with will be exponential in size, so no way you can actually deal with this numerically. This means that this will only work as long as you think of some clever geometric structures that are not only appropriate for the problem that you are studying, but that are also tractable because they are somehow nice. And there are ways of doing this. I don't want to get into detail, but it's again to give you some perspective of what happens when you start to considering different settings. Different problems arise and different ideas arise. Okay, so this is what I wanted to say about the machinery that allows to make you the definition explicit. The next thing that I want to do is to briefly just show you what settings people have been studied, and I am sure I missed some of them, but at least this will give you a partial idea of what happens in the current literature. And another thing that I wanted to say is that, okay, so the way I motivated the Matern Gaussian processes and Matern kernels was that let's just start generalizing the Euclidean thing, which is good, in a way which works, which you might criticize, but I want to say you right away, to tell you right away that this is not the only way to motivate this class of kernels. For instance, typically you can build them up from just two assumptions. The first assumption is this generalized stationarity, so that you have some class of symmetries, and you're only interested in considering kernels that are invariant with respect to these symmetries, so general stationary kernels. And the second assumption is the assumption of smoothness. So basically, symmetries plus smoothness plus certain degree of smoothness inevitably leads to Matern kernels, or kernels that are absolutely equivalent to Matern kernels in the way that you use them. So I introduced them in this way. There are other ways in which you can do this, but yeah, just to give you even more foundation to this idea. And now the other settings. First, I want to show you a couple of manifold settings. So the simple manifolds, and in particular meshes, which are like approximations to two-dimensional manifolds. This is something that you can do. And this is something that already goes a little bit way back. There are newer studies that consider manifolds which are somehow ideal. Something that Alex mentioned, the manifolds that sort of mathematicians study. And they possess certain nice structures that allow you to go into dimensions much, much higher than you would be able to handle if you just discretize stuff. And these manifolds are useful, and I will show you an example of why they're useful. There is another example. It's also about manifolds, but also about not just modeling scalar quantities, but modeling vector fields, which is like two levels of geometric structure. First, in the way that your input domain is not Euclidean. Second is that modeling a vector field is not at all the same as just modeling a vector valued function on a non-Euclidean domain, because you have the requirement of vectors being tangential, for example, right? And phenomena that only happen for vector fields, like, for example, Harry-Ball theorem that says that every vector field on top of the sphere will have whirl. And this is something that very naturally can be used for modeling wind velocities, for instance. There are settings also concerned with graphs and their like. So, for example, I was talking about graphs and implicitly just translating this into the node set of a fixed graph. You might be interested in doing a different thing, but considering an edge set of this graph and flow type data there. Here is this example is, for example, is about currency exchange rates. And there are very interesting things you can do here and interesting connection to the vector field world. There are metric graphs. There are cellular complexes. And finally, spaces of graphs that I mentioned. Although this is like the thing that I'm showing for spaces of graphs is very, very incomplete. It's just something that you can do in this very broad direction. People also study the question of what if I want to do this geometric modeling and say, I assume that my data lives on a manifold, but I don't know the actual manifold. How can I approach this problem? So this I refer to as implicit geometry, and there are studies that deal with this. There are interesting complications arising in that particular research direction as well. And my personal opinion is that the largest problem here is the absence of good GPU implementations of certain linear algebra algorithms, specifically the algorithms for computing top K eigenpairs, which are really lagging behind some of the other tools that are getting increasingly available on GPUs. So this, and of course, there are also theoretical results. There are theoretical results which are simple, like the ones that sort of the kernels that I was talking about respect the symmetries, but there are more sophisticated ones that mirror the guarantees or the theoretical behavior overall that you have for the Euclidean maturing kernels in the geometric settings. In particular, for the manifold setting, there are studies that talk about maximum likelihood hyperparameter estimation, the consistency of this. And what's very interesting here is that there is actually an open problem still, I believe, in the Euclidean case concerned with the consistency of hyperparameter estimation, which is solved for all n, for all d less than or equal to 3, and for all d larger than 4, but not solved for 4. But if you consider this for compact manifolds, it is solved for 4. It's just an interesting detail. And there are also studies that, for example, bound minimax errors, something that reproduce sort of the behavior of asymptotics of the traditional maturing Gaussian processes in geometric settings. These both are about the manifold case. The other cases, I think they're theoretically not so well studied. Also very much encourage you to join in on to studying those. And this finishes up by a largest section about deep dive into geometric Gaussian processes. And I go to a couple of much smaller sections. First one is about emerging real-world applications of geometric probabilistic models. First one will show you that these ideal manifolds can actually be useful in practical applications. And this I want to do by showing you this application in robotics, and specifically in Bayesian optimization of control policies of robots. It turns out that some of the policies you may very naturally parameterize by physical quantities that naturally live on manifolds. And these are, for example, a joint posture of a robotic arm. Maybe you are parameterizing your policy by an initial posture of some some part of the arm or something like this. If your joints of the arm are circular, and if you have an arm constructed from many of those, you have a product of circles, which is a hypertorus, a manifold. There are other physical quantities that naturally occur in physics and therefore in robotics as well. Of course, rotations, you might be able to parameterize something by initial rotation or rotation at some specific part of the task of interest, which is rotations are objects that lie on a manifold, either on the maybe three-dimensional quaternionic sphere, or they can also be modeled by elements of the Lie group SO3, which is a manifold. Or finally, there are these notions of manipulability ellipsoids. Ellipsoids are parameterized by positive definite matrices, which lie on in the manifold of positive definite matrices. So the paper I'm citing here studies what happens if you use geometric Gaussian process models instead of the Euclidean Gaussian process models, and also geometric optimization of acquisition functions to boost the performance of Bayesian optimization in order for it to converge faster, which is a very much very interesting for practical purposes goal, because, for example, if you're fine-tuning a policy after installation of a robot on a factory, you want to do this quickly and you want to spend as few cycles of this robot as possible. And it shows that building the geometry, which is inherent in the problem, into the models that you use, into the optimization procedure as well, helps to boost Bayesian optimization, in this case, considerably. Another application that I want to show you here comes from the field of medicine, and it's concerned with modeling atrial activation maps. Basically, modeling certain quantities of interest on the surface of human heart, which is of course individual for every patient, and which can be somehow mapped using non-invasive techniques, and use this geometry to probabilistically interpolate measurements obtained from an invasive technique, therefore minimizing the need to the time of the procedure where you sort of insert the catheter into a patient and gather the information by probing the heart, improving the quality of life of a person by not making them suffer for such a long time. So this is something that people do, and also very exciting to see applications of geometric probabilistic modeling in medical applications. And this one and the last one are all about geometric Gaussian processes. And this one in particular is also interested in the way that it came up with a Matern Gaussian processes on meshes in an independent way, and so which sort of testifies to the naturalness of the idea. The last thing is about deep ensembles based on graph convolutional neural networks. this is actually a very very interesting problem to try and solve using Bayesian optimization. You have some engineering shape which you want to optimize in order to improve some performance characteristics. Like, for example, here you optimize the shape of a car for drag. There is this company, an EPFL spin-off, which is trying to use this deep ensembles based on graph convolutional neural networks to make this work somehow. And this is an example of actually deep ensembles of not graph, but geodesic convolutional neural networks. I'm sorry. This is another sort of type of model in geometric deep learning. Okay. So yeah, this is an example where deep ensembles in geometric settings actually do something, right? So there is these applications and there are other applications, but this is sort of an emerging field. So what I really encourage you to do is to join in and tackle the problems that you deem interesting. And also join in on the theoretical part because there is lots and lots of things to do. Finally, I want to very briefly go through the software part. First of all, there is the QR code for the implementation of the experiments at the very beginning. And there will be also QR code at the very end of the slide, so you don't have to do this right now. The stack that I used in order to implement this was using PyTorch geometric for graph neural networks. This is the most sort of popular library for geometric deep learning, and in particular for graph neural networks. I used Pyro to make neural networks Bayesian. I used GPyTorch to drive basic Gaussian process routines, and I used geometric kernels that implements hidden maturing kernels on geometric settings to drive geometric maturing kernels. And I want to focus a little bit on this. So this is a library that actually myself, Alex, and a couple of other very important collaborators developed. And it's available right now. You can use it to hopefully very easily drive your Gaussian processes on geometric settings. It's as simple as this. So if you want to, say, compute a kernel matrix on a sphere, what you do is just create a space, a sphere with one line of code. You create the kernel and initialize its hyperparameters with another 2 lines of code. And then you just compute and print the kernel with another 2 lines of code. So 5 lines of code give you the kernel matrix of the maturing kernel on the sphere. Here I have also a table of the tools that you might want to use if you prefer other framework like JAX or TensorFlow, and to implement something similar to what is implemented in the notebook that I used for the first part of the talk. Here I know that the geometric kernels library just supports all of these backends, so you can just use it for all of these applications. And another thing is that in geometric deep learning, there is a lot of libraries that are very well maintained for graph neural networks. But if you are going to do something else like geodesic neural networks, it's more like there is a lot of small libraries of variable degree of support quality and maintenance quality. Okay, so now for summary, I just want to quickly pass the mic to Alex, and then we'll be able to take a couple of more questions.
Yeah. So this is really the conclusion for the tutorial. But just to go briefly over everything that we discussed and kind of get us to the point where we're ready to talk about questions. What do we do? Well, we talked about geometric machine learning, which is becoming sort of increasingly popular, particularly in sort of the geometric deep learning world these days, although there was also sort of a previous wave for kernels on structured data where the random walk kernel that you saw came from. And yeah, the main thing that we want to tell everybody is that geometric probabilistic models are these days an emerging research area. In particular, we have geometric Gaussian processes that we talked about in some detail. These are quite solid off-the-shelf sort of baselines that you could try on a variety of problems where you want to do predictions and then something with uncertainty. And they're still under active development. There's lots and lots and lots of stuff to do, both on the sides of theory, analysis, developing models for more settings, developing better computational tools, and developing applications for all of these techniques for various practical problems where I think we're only beginning to scratch the surface. Maybe another thing that deserves mention is the decision-making side and things like Bayesian optimization in geometric domains and connections sort of with regret analysis and things like bandits and sort of areas like this too. And finally, which is part of the reason I decided to come up, is Slava is moving to the University of Edinburgh to start a lab there, and he's going to be hiring PhD students. So if you know anybody who's interested, you should tell them to talk to him about working with him. I'm actually very, very, very excited to see him kind of move to that career stage. Hence the hype. And yeah. And with that said, I wanted to, well, I think both of us would like to thank everybody for your time and listening to some of these ideas that I hope you found exciting. We're both on Twitter. You can find us there. There's a QR code for the slides. The slides are sort of in the form of active maintenance, and we're going to populate them with a bunch of references from both the various papers that we talked about during the tutorial, as well as other sort of papers that we came across but didn't mention. But give us about a day and the references will be there together with a button to easily get to them. But in the meantime, if you want the notebooks, those are all available. The slides are available. They're online. They're on my page. They're on his page. If the UAI organizers infrastructure supports the form of slides that we use, they're going to be on the UAI page too. And thank you very much for taking the time to come here and listen to us. And we're happy to take questions.
Any questions?
Yeah, so all along the tutorial, you talked about the importance of geometry, but you assumed that the geometry was enough. And you have problems with model on top of that. But what if the geometry itself is got uncertainty about the geometry?
So this is a very good question. And the short answer is that people study this. Two of the papers that Slava showed towards the end were on implicit manifolds. And some of the works in that space are exactly dealing with this question. And just to give a flavor of what like a typical question kind of looks like that papers like this do, is you can study what happens if you have data that comes from a manifold that's unknown, and then you just get that data and you make some kind of nearest neighbor style graph, and then try to sort of put together a graph Gaussian process over that graph. Well, then the question you can ask is this going to be similar to the sort of limiting manifold Gaussian process you'd have if you had sort of an infinitely large amount of data? And if so, how quickly? What are the errors? How well does it work in practice? Are there tricks to make it work better in practice? And all of this kind of stuff is exactly, I think, an example of like the kind of work that's under active research. So it's a really good question. I don't know if you want to comment too.
Just one factual thing. So if you try to Google Bayesian graph convolutional neural networks, then the papers that will come up probably is something about the uncertainty of the structure of the graph. So in that community, this is there is actually it's actually hard to find a paper that studies a Bayesian graph convolutional neural network for a fixed graph, because they're mostly trying to tackle this problem that you mentioned. So yeah, also people coming from this direction are naturally interested in this type of problems. Any other questions? Yes, please.
And you said that they're kind of motivated by your smoothness, and then also this thing about stationarity. I'm assuming it's something to do with like the stochastic differential equation it comes from. But I was wondering if there's like sort of an intuitive reason this traffic, data set was particularly amenable to entanglements. Maybe like there's a dense region of traffic and it dies out.
So my intuition is that coming up with a model which is good for both prediction and uncertainty quantification is harder than combining a good predictive technique with a good probabilistic technique, like picking an off-the-shelf architecture of graph convolutional neural network and an off-the-shelf MCMC engine for standard type of initializing Bayesian neural network doesn't work as great as it would if you would really invest into coming up with the proper architecture and proper ways to run this. And it seems that there is just much less effort and much less available resources that you can use outside of the geometric Gaussian process world if you want to just sort of use a model without too much effort. So yeah, it's sort of that the supply is limited for the others. I don't know.
I was going to say, I kind of interpreted the question in a slightly different way, which is just to say that in some sense, you can ask, there's no notion of like a shift in variance on the graph or something like that. So why should we expect the kind of behavior on the graph to be similar to behavior of like the manifold models or of the Euclidean sort of kernels of this kind? And the answer I would give is, well, you're right. A priori, like, unless you've tried it, then they might not do that. But what happens is when you take graphs that, like a grid-based graph or various of the other examples, what you see sort of over and over in them is that what tends to happen is that the sort of dependence decays kind of roughly as you take nodes further away. Of course, it doesn't exactly do that because it's not distance-based, but it somehow behaves in all the similar ways that you'd want a distance-based thing to behave when you look at it empirically. And so really, I think it's motivated by empirically, they behave similar to the Euclidean models, and the Euclidean models do kind of the things that we want them to do, at least in those cases. So that's kind of at least how, in my mind, the logic goes. I see a question way in the end over there.
Where you don't have to define it for the moment, and any kind of I don't know actually there's some action here where they make it at like symmetry. I don't know, right? Like you learn it.
So thank you for the question. The question, again, for just to try to repeat for people online, involved basically, in some sense, how do deep kernels fit into the whole story? And could this be like an interesting way to do sort of the implicit manifold setting where you don't know exactly what's the manifold and things like this? Did we find much on deep kernels in geometric setting when we did our lit review? I don't remember actually seeing so much about this.
No, but I think like if you think about implicit geometry, then probably your setting is a priori not a geometric one. You're just sort of hoping that by inferring some complicated model. In the middle, you also infer the geometry. It's like when you are training a deep neural network, the second to last layer is supposed to somehow infer an embedding and perhaps maybe even manifold geometry, if you call it this way. So yeah.
I was going to say, because partly it could also be active research. You should study deep kernels for these kind of things, because I think, I mean, I was asking partly because I don't remember seeing so much. That could be kind of for whatever reason, not that explored topic, or we missed it.
Yeah.
So try it out.
I can just suggest a little bit of personal opinion on that. Basically, sort of what we were showing is really concentrated on the setting when geometry is really known or can be formalized somehow, and then you are trying to leverage this in a reasonable way to create better models. The setting when you assume some implicit geometry is quite different, I think, is much more complicated, because when you're doing uncertainty quantification, you have to have some global knowledge about your space. Otherwise, when out of distribution samples start coming along, you don't know they're out of distribution and you do weird stuff. This is what often happens with neural networks, and like even deep ensemble, you provide it with out of sample inputs, it behaves badly. When you are trying to infer this implicit geometry from the same data you are training your models on, this might be not enough, because this doesn't give you information about these global parts that are further away, right? It might be an interesting direction, but you would certainly need to overcome some pretty hard challenges.
And I think, if I'm not mistaken, we are out of time. So in this case, if you still have questions, please come talk to us. We're going to be around for a little bit. And I wanted to say thank you again, everybody, for your time and attention.